So thanks everybody for joining us here towards the end of March and for another Space VT seminar. For those probably down the road following online on YouTube, I have been way behind on posting any of these online, but I will, let's say I'm recording this and will eventually get it posted. I've had a lot of things going on so far this semester that has just kept me from getting to that. But today we have Reece and Kevin. Okay, I was wondering those two. So we have Reece and Kevin here from the Orbital Launch Vehicle Team at Virginia Tech, and going to describe their experiences and probably challenges getting to space. That's a pretty good summation. So I'll start this slideshow, and without further ado, I'll let you all take it away.
Right. Hello and welcome. We're members of the Orbital Launch Vehicle Team at Virginia Tech. And today we're going to talk about the collegiate rocketry scene, as well as what it takes to get a collegiate rocket into space with a space shot flight, as well as our design team's progress towards that feat. Today, we're going to go through a couple topics talking about the collegiate rocketry team and the history of collegiate space shots, sort of who's going for it right now. We're going to talk about our team, the Orbital Launch Vehicle Team, what we do and the recent progress we've made, as well as our future plans toward an eventual space shot and among our other future goals. And then we'll open the floor up for questions at the end. So we just wanted to start out giving everybody an idea of what the collegiate rocketry scene is like across the country. You can split the collegiate rocketry teams into two main categories: competition-based teams and goal-based teams. Competition-based teams, which make up the majority of the teams, despite the logos seen on the screen here, really shoot for the design specifications and altitude specifications of yearly design competitions. They revolve their team's purpose around competing in these competitions for either altitude or testing new technologies. And then every year they start a new design to compete in the next competition. In contrast, the goal-based teams are more for research and development of complex technologies at the collegiate level. For example, liquid biopropellant engines and things like that. And what they do is they progressively work towards the research of high altitude launch vehicles, whether that be researching things like hybrid engines or trying to, like what we're going to talk about today, surpass the Karman Line and reach a space shot.
All right, just to talk a little bit about what a space shot is. So a collegiate space shot is the pursuit by a collegiate design team of a successful launch beyond the Karman Line, and that's greater than 100 kilometers altitude into space. It's a very challenging goal, very lofty goal. Right there, we have a list of some current teams from around the country who are undertaking this challenge. You can see that USC RPL has been so far the only team to successfully launch a space shot. The picture there on the right shows their Traveler 4 launch vehicle, which successfully launched to, I believe, 107 kilometers back in 2019. So that's a very impressive feat. That launch vehicle was basically a large solid rocket motor in the R impulse class with a composite tube around it, a nose cone, and some avionics. It was designed for simplicity and maximum power. That was a one-stage launch vehicle. So, going for a space shot demands some key design choices, and we've compiled those into a list of necessary technologies that will be needed. The first and really most important is an experimental high-power propulsion system. This could either be a solid rocket motor, a hybrid rocket motor, or a liquid bipropellant engine, though the vast majority of collegiate teams, for safety and budgetary reasons, elect to use, including ourselves, a solid rocket motor system. for their launch vehicle. Long-range communication systems are necessary to obviously communicate with the launch vehicle from high altitude. A composite and metal structure must be optimized for drag minimization in order to withstand aerodynamic and thermal loads while flying in the hypersonic regime. A robust recovery system is necessary, obviously, to make sure that the launch vehicle reaches the ground safely. Robust safety infrastructure is possibly even more important than the propulsion system because when you're dealing with these high amounts of energetics that could pose a serious threat to the lives and safety of team members, you really need to have your safety house in order. Launch site with necessary FAA clearance. You can't launch a rocket to space from just anyone's backyard. You need to go out somewhere that is capable of accommodating such a launch. And a launch tower capable of handling the takeoff loads of a vehicle, which will likely be around 300 to 400 pounds. On the right, there's a picture of the 60-foot launch tower at the Friends of Amateur Rocketry, or FAR launch site in Mojave, California. That launch site is one of 2 or 3 places in the United States where you'd be able to go for a space shot.
So next we wanted to talk a bit about where we stand in this collegiate rocketry scene and what we actually do as a team. Kevin and I have both been on this design team for a very long time. It's a fairly young design team, only been around under 10 years or so. I am a current co-president. Kevin is a former co-president of the team, and we've both been on the team for the majority of the team's lifespan. What we do is we're a collegiate design and research team with the goal of utilizing a student-run organization and with the help of engaged faculty to reduce the cost of academic payloads to space while developing design and experience problem solvers. Really what we do is we would like to make it way more accessible to get student satellite payloads into space. Right now, if you are a student design team trying to develop a CubeSat or any sort of space payload, it's almost always prohibitively expensive to launch those payloads into space, especially frequently enough to do frequent and meaningful research. We'd like to lower this cost and make it much more available for these student teams to launch their payloads into orbit and do the research that they've worked so hard when developing their satellites to do. We have short, mid, and long-term goals. Our long-term goal, as we said, was to deliver a 5-kilogram payload into low Earth orbit. Our midterm goal, which is the topic of this presentation, is delivering a 5-kilogram payload beyond the Karman line to do our space shot. Right now, our progress towards this goal, our short-term goal, is design iteration and verification in order to really rigorously verify the designs that are necessary to reach the space shot and eventual orbit. Our team is split up into 6 sub-teams in order to split up the workload and make sure that each element of this very complex design goal is really split into people that have expertise in specific areas, because there's a lot going on in these launch vehicles, and we really need the best and brightest engineers in order to make this mission possible in every way.
All right, so I'm just going to talk a little bit about our team's organization. We have 6 different sub-teams, the first of which is avionics, which really deals with the flight computers, long-range comm systems, coding, and the electronics bay, which is the structural part of the rocket that houses all the flight computers and transmitters and things like that. The picture below that shows our long-range comm system undergoing testing by the avionics sub-team. Our business sub-team acquires sponsors for the team, runs the social media, and does budget management. And, business may kind of be an afterthought, especially at, an engineering presentation, but without funding and support, we really wouldn't be able to do any of this. So a very, very important piece of the puzzle right there. Launch operations is a team dedicated to making launch procedures for each launch vehicle, having dedicated safety officers to ensure that everything is safe at all times, and then designing our launch tower, which we are just getting started with. The next sub-team is propulsion, and they do solid rocket motor design and integration, static fire testing, which will be starting up here probably pretty soon, and then nozzle optimization, which is important for high altitudes. Our structure sub-team does CAD and FEA work on our structures. They do the main manufacturing of like the airframe and the nose cone, main structural components. They also design the recovery systems and perform testing on those systems. The picture there shows the integration of the test turkey launch vehicle at Kentland Farms. Our trajectory and aerodynamic analysis sub-team does flight simulations for each of our launch vehicles and performs CFD on either a specific element, which in the GIF there you see a fin profile, or the full launch vehicle as seen below that. They also do our fin and nose cone design optimization.
So now we can talk about the recent progress, where we are right now on the team. Our most recent success was the launch of our test turkey launch vehicle. Test turkey is a high performance subscale test rocket designed to verify the elements of Hoki 0.75, our eventual space shot vehicle. This is a single stage launch vehicle that flies on solid propellant and is 89 inches long, made completely out of aluminum and fiberglass construction for weight optimization and cost. It's flown twice now successfully. The L1720 motor was our first launch at Kentland Farms right here, right near Blacksburg in 2020. And that launch went up to 5,900 feet. Our most recent launch out of Mojave, California at the Friends of Amateur Rocketry launch site, which we mentioned earlier was a potential space shot location, was launched on an N1000 motor to 29,500 feet in 2021. This actually broke the unofficial altitude record for rocketry teams at Virginia Tech. The previous record was also held by us and was achieved using our Hoki 0.5 launch vehicle that launched to 17,000 feet. And we hope to continually break these records as we progress higher and higher. You can see the picture on the right on the top is our test turkey launch vehicle as it's taking off at the FAR launch site. And the bottom picture is the team that was loading the rocket onto the launch rail at FAR, along with our range safety officer and advisor, Bob Schoner, on the left. Here we actually have a video of the launch of Test Turkey. This was a really exciting moment for the team. We worked really hard to get to this, and the fact that everything worked as we had planned it on this flight, and we had a successful recovery after, was really exciting for the team and a big step for us towards our final goals. Yeah, go for it.
All right, awesome. So with Test Turkey completed and our team looking onto new launch vehicles and a new testing and development plan, where do we stand on those key technologies that I mentioned earlier? Well, with the experimental high power propulsion system, unfortunately right now there's a lack of infrastructure and support at Virginia Tech for testing and developing solid rocket motors and propellant, even at a small scale. So we have kind of run into a snag there. We do have friends within the industry who could cast motors for us. However, those would be fixed propellant mixtures that we wouldn't be able to test or change or optimize. So one of our design variables would be constant. Therefore, we would pose some challenges, but not anything that wouldn't be able to be overcome. Our long-range comm system, we had a picture of that earlier. It's being tested and developed, and we hope to launch that on our Skipper 2 launch vehicle, which we will mention in a few slides. Our composite and metal structures, we're currently in the process of developing these structures in-house and manufacturing them. On the right there, you see a little GIF of, actually that's Reece and I in the background. It's kind of hard to tell, but we are filament winding a carbon fiber airframe at the AEDL, the Advanced Engineering Design Lab site out by the CRC. The recovery system, we are working on that. We have a new design for the recovery system that's a little more space optimized. The safety infrastructure we definitely have at this point. We have pages and pages of launch day procedures and safety protocols. We do have a launch site with the necessary clearance, like we mentioned. FAR is a great option. And then a launch tower capable of handling the takeoff loads. We are just kind of starting to get into that now that we're looking towards progressing to larger launch vehicles that maybe could be handled by the launch tower provided by any given launch site.
Okay, so now we can get into what are our future plans? How are we going to progress towards this ultimate goal of a space shot and eventually delivering payloads into orbit? We really think it's important with such a large feat to follow the proven design methods and construction methods that are placed by systems engineering. This is sort of a diagram of the average systems engineering process that's followed a lot in the industry, and we've adapted it towards our specific milestones. Really what we need to do in order to achieve this is to create these milestones that you can see here: a single stage stub-sail vehicle, two-stage subscale, single stage full scale, and then eventually our two-stage space shot. Within each of these milestones, it's really important that we iterate our design until we reach our defined parameters of success. We spend a lot of time really meticulously defining these failure and success parameters. Success doesn't exactly mean a successful launch that goes up and comes back down, and failure doesn't mean the rocket blows up or falls out of the air. We really make specific parameters and goals that we want to reach for each vehicle, and we iterate that vehicle and improve the technology until it meets our final definition of success before we move on to the next stage. Currently in our design process, as we'll talk about soon, we are at the one-stage subscale stage of this path to orbit and space eventually, and we'll get into the specifics of the launch vehicles that fit into each of these stages as we move on.
All right, so I just want to talk a little bit about, what those launch vehicles actually are within our Path to Space mission plan. So Skipper 1, which is named after the cannon that fires the football games, which happens to actually be built by Homer Hickam, who's a kind of a rocketry legend. So Skipper 1 is a single stage subscale vehicle of Hokey .75. It'll fly on J through L impulse motors, and we're looking to get between 5,000 and 20,000 feet of altitude out of this vehicle. The main goal here is to solidify our in-house manufacturing capabilities, which will thereby reduce cost and time to flight, and also create a test bed that can be used for future design iteration. Skipper 2 is just Skipper 1 with a booster stage installed below it. You can kind of see the actual configurations there representatively at the bottom right. This will be a two-stage subscale vehicle of Hokey .75. The sustainer or second stage will fly on J through L motors, and the booster or first stage will fly on M through O motors. We are going to try to implement a sustainer coast phase. So between the stages separating and the sustainer stage igniting, there's a delay, and that optimizes altitude. That's a major design challenge that we're going to try to work out with this vehicle. We hope to get around between 20,000 and 60,000, maybe higher, feet out of this vehicle. And the goals here are to solidify our staging capabilities, which once again is really a major design challenge here. And the whole reason we're doing staging is because our long-term goal of orbital flight demands a multi-stage vehicle, and also to further develop our in-house manufacturing capabilities and iterate those design elements and variables that we had been doing so with Skipper 1 on a two-stage vehicle. And this launch vehicle setup actually brings about a pretty interesting design space, which has been represented qualitatively here. So we have 3 different motors that can be used and swapped out within the second stage of the sustainer, and also 3 different motors that could be swapped out within the booster stage. And these are just impulse classifications. Within each of these impulse classifications, there are often hundreds of different solid rocket motors off the shelf to choose from. So, you know, a full design space analysis for this would be rather complex, but for our purposes, this combination of configurations brings about a matrix of 9 different design spaces, which vary in altitude, maximum speed, and just the overall how demanding the flight profile of the vehicle is. And that will allow us to select different configurations for different launch sites, which may have different altitude requirements or safety requirements, or to select either a low altitude version for testing a certain component or the maximum altitude version for testing a certain component, or somewhere in between. We have a lot of freedom with this design space, and we're hoping that that will allow us to really branch out and not be constrained to either launching at home really low altitude or launching out in the desert across the country at really high altitude.
Okay, so as you saw in the flow chart for our systems engineering process and mission plan, after Skipper 2 comes our sustainer stage of the Hoki 0.75 eventual space shot that we've dubbed the Hoki P. This will be a single stage full scale rocket that will fly on a experimental P motor that we will get custom cast. And this will serve as exclusively the sustainer stage of that space shot vehicle. Our goal is to get this vehicle above 100,000 feet. And really, this is a really important step for us because it will allow us to develop the sustainer for our space-capable launch vehicle and make sure that we can do this within reasonable costs and the timeline constraints. And it will verify our designs for our space shot at the full scale. If the sustainer works as we plan it, it will be a really big step for us towards adding the booster onto the stage, which gets me into our next vehicle, the Hoki 0.75. This vehicle has been long in planning, and it is our 2-stage space shot vehicle. It will fly as of now from a Q impulse to a P impulse motor with for respectively booster and sustainer. And our goal, as we said earlier, would be to surpass the Karman line at 100 kilometers. And this will allow us to test our long-range communication systems, which for our first launch will serve as our 5-kilogram payload that will deliver on the Karman line. It will fully verify our space flight capabilities and our ability to utilize high-altitude avionics and recovery systems. This really is the biggest step towards our eventual orbital goal, as it will verify our ability to get a rocket into space, because obviously we cannot even think about delivering something to orbit until we verify that we can safely deliver a payload into space and recover it safely as well. In the next slide, we have a little bit more specifics on this Hoki 0.75 launch vehicle. We've already begun to develop the ConOps for this vehicle, as well as preliminary CAD models and a lot of analysis on the structure and performance of this vehicle. As we said before, the main goal of this vehicle is to deliver a 5-kilogram payload beyond the Karman line and verify the iteration of design, funding, and launch techniques. If you look to the image on the right, that is the general ConOps for this vehicle. And that's just pretty much a standard 2-stage launch vehicle concept of operation, in which we will drop our booster stage mid-flight after the motor burns out. And then our coast phase will allow the sustainer to continue on and eventually ignite the second motor and reach the Karman line and deploy first the drogue parachute and then the main parachute as it comes back to the ground for us to safely recover. We have some very specific design constraints for Hoki 0.75 on top of our main goals. We definitely want to utilize 2 stages in order to, as we said before, enable our orbital flight. We've restricted ourselves to solid propellant for the simplicity and safety. There's a lot known about solid propellant in the industry, and so we that allows us to have a reliable engine that we know will work as we expect it. The implementation of custom data transmission systems, which is our long-range comm systems that we showed in the beginning of the presentation. And two of the most important ones, adhering to launch day procedures and utilizing robust safety measures. It's really important that we adhere to the launch day procedures that we spend so much time developing so that everything goes smoothly. You never know what's going to happen on a launch day. And if we stick to our launch day procedures carefully, every thing that could go wrong, every process is accounted for so that we can make sure that everything goes smoothly.
All right, so in conclusion, while spaceflight at Virginia Tech may seem like some far off, crazy ambitious goal, OLVT is really taking some steps to make it a reality, and not only a reality, but a safe and feasible financially and logistically reality. So we are utilizing a systems engineering approach to design and iteration, which is fundamental really for any engineering project. We are methodically developing the necessary technologies for spaceflight to full confidence. So we're not just, slapping together a launch vehicle based on a few simulations and then sending it and seeing if it works. We're really taking our time to test and iterate at a small scale and improve those up to a larger scale. We're utilizing in-house fabrication and testing to reduce costs and time to flight. Like we mentioned before, you can't just buy some of these components off the shelf, like the large rocket motors or the airframes or the custom nose cones, fins, and things like that. So we really need to utilize in-house manufacturing and testing for some of those design elements. We are rigorously documenting our methods and results to build team knowledge base over time. This is really important, and it's something we hadn't really touched on so much yet, but in a collegiate design team, your employees leave after 4 years when they graduate, or even sooner, depending on when they join the team. So documentation is really key to making sure that the team continues to progress forward, even if people who were leading it previously have since graduated. We are also continuously implementing robust safety measures and launch day procedures at all times to make sure that all of our testing and launches are run safely and in a smooth, organized fashion.
And this list really highlights what makes OLVT special, what sets it apart from the massive pool of design teams, specifically rocket design teams across the country. We really try to operate very closely to how aerospace industry startup operates, not just with our goal of delivering payloads to orbit, which is what aerospace startups do, but in our methods of doing so and how we organize our team. Really, this system of iterating designs, developing technologies over time, building things in-house, and making sure we're keeping track of funding and making sure that each area of design is specialized is really how larger design companies in this industry operate, which allows us to give our members really valuable industry experience, not just in things like testing and designing and CADing and manufacturing, but also since we are consistently presenting to our faculty board and writing research papers on each semester on what we've worked on, we're giving people the skills of how does a large design team or company operate? What does it take to make something so large and so expensive run? And how do you express your progress and what you're working on and your confidence in your designs to people in authoritative positions that can dictate whether or not these designs go through. So it really offers unrivaled experience to the members on this team, and they can go out with their experience on this team and participate and contribute a lot to the aerospace industry after they leave.
Yeah, and right now and for the foreseeable future, we are going to be implementing our Path to Space mission plan. We've already started the design for Skipper 1, or at least the first iteration of that vehicle. The design is almost completed, and we hope to launch that either very late this semester or early next semester, depending on a variety of factors. But we're really excited to move ahead with our in-house manufacturing methods and really push the boundaries of what's possible at Virginia Tech. And yeah, we're really excited to be in the position to do this, and we wouldn't be here without the support of our sponsors and also the university. So yeah.
That's all we got, and we can open up the floor for questions now.
I have a question. Can you go back to the slide where your launch vehicles were there, Skipper 1, 2? Yeah. So in the first two vehicles, Skipper 1 and Skipper 2, the fins that you have on the is backwards swept, and the next two are like zero dihedral. So is there a difference?
Right. Yeah. So these are purely representative images. That was just an artistic choice more than anything else. The reason you would have the backward swept fins on the sustainer, though, is because they are better optimized for high velocity.
And what kind of grain profile do you use in your solid rocket model?
That's a really good question. Right now, since we can't really cast our own propellant here at Virginia Tech, as of now, we buy stuff off the shelf. The main propellant grain geometry is a Bates grain. And then if you move that Bates grain like to the side, it's a moon burner. So our most recent test turkey launch on the N1000 was a moon burner geometry, which gave us a burn time of around 14 seconds. For Hokie 0.75, we planned on using a Finicil grain geometry for the booster to push us off the launch tower fast enough, and also past like the transonic range. And then in the sustainer, use like a moon burner or something like that to slowly push up to altitude.
And how do you perform this staging? Do you have a push motor that pushes the booster stage further, or?
Yeah, that's a really good question. So what we've done in the past is simply just couple the two stages, and then when the sustainer motor ignites, it separates them. We want to move away from that because that removes the possibility of having a coast phase where you separate the stages and then ignite the sustainer motor, which will, like I said, give you better altitude. So separating the stages is something that's like a main key design choice that we're looking into right now. There's a lot of methods you can use, like springs. You can use push motors, like you said. We're really just kind of evaluating that right now, and figuring out what the best method is for us. And that's, something that'll be iterated over probably multiple times before we're like fully confident to move up to the space shot.
I think talk to some of the other universities about this and see what their general process has been.
Yeah, there's a lot more variety than you would think across the teams. Right now, I mean, obviously, as we said earlier, the USC team decided to just throw a very large motor into a single stage rocket, and they were successful with that. There are a lot of other teams working to do this space shot attempt. For example, the Boston University Rocket Propulsion Group, they are trying to do this on a completely liquid motor, which obviously takes longer to develop, but eventually allows for a lot more freedom in your design after you've developed those liquid technologies. And then other teams are using hybrid motors as well. So there's a lot going on, and there's definitely a lot of resources in terms of places to take inspiration from. But there's a ton of variety in terms of how people are trying to tackle this space shot goal.
Yeah.
That answers your question.
Yeah, definitely. And another thing I would add to that is actually the location in which the team is based. So for example, like somewhere like UCLA or Stanford or USC, they're like a hop, skip, and a jump away from like going out to the middle of the desert and launching a huge rocket. But for us here in Virginia, like it's an ordeal to get like personnel and hardware out to the desert for a launch like that. So like that kind of necessitates a level of simplicity in our design that may not be so strongly needed if you're at another university in a different location. It's just unfortunate because there's really no like spaceport in Virginia. I mean, there's NASA Wallops, but for like a lot of reasons, there's not going to be like student launches happening there. And yeah, like it also depends on whether your university is comfortable with letting your team make certain design choices, especially in terms of like the propulsion system. So like Reece said, like Boston University RPG, they're doing a liquid propellant system, and Virginia Tech is for better or worse a very risk adverse organization, and they do not like the idea of students undertaking a liquid bipropellant project. And not to mention that, but we also don't have infrastructure, like a testing site that could accommodate something at that scale and complexity here yet. Where the hope is that that'll be developed as more people are interested in doing this at Virginia Tech, and that more people are on board with like the mission plan. But for now, we're really reliant on some of our like industry friends and sponsors and things like that.
Yeah, it's really dependent on, there's a lot of different factors that go into how far a lot of these teams are. Some teams, we've only been around for under 10 years. Some of these teams have been around for up to 20 years. And then like Kevin said, the amount of testing infrastructure that exists is really important as well. Obviously, we have the wind tunnel, and we're lucky enough to have a space like Kentland Farms right now. Besides that, we're really limited here in terms of large spaces to do things with highly energetic materials, whereas other teams have entire fields and properties dedicated to testing liquid propellant, or in the case of schools like UCLA, they're able to pretty easily transport the large equipment needed to big places like Mojave, whereas it was already extremely difficult to get our subscale rocket tester heat all the way to California. We actually had to drive it out there because you can't take a rocket on an airplane. And it would be even more difficult, probably prohibitively difficult, to get the necessary materials and equipment needed to get a liquid motor out to California. But it's really just dependent on the situation of a lot of teams, which is very cool. It's cool to see all these teams working towards the same goal, but doing it in completely different ways, depending on their resources and their team's expertise and where they're drawing their support from. So it's really exciting. I wouldn't say industry, but scene to be in terms of collegiate rocketry going for space shots.
Yeah, and the last thing I would add to that is obviously like financial support and funding. We've been very lucky with some really supportive sponsors and donors over the past few years since we were started in 2016. USC RPL, for example, has been very, very lucky and gotten like donations on the order of perhaps millions of dollars in some cases. So if we were to fall on those kinds of funds, perhaps like we would not be so concerned about like reducing all of our costs so much. You know what I mean? Some design choices may be a little bit different depending on how much funding and support each team has.
Dr. Bailey, I see you're unmuted online. Did you have something?
Definitely. First, great job and great presentation. The work you're doing is awesome, and we're all really proud of you.
Thank you.
Sure. Could you've been hinting at this some, but just how does it work with you in the university? Do you get faculty support? Do you have a faculty advisor?
Oh, totally. Yeah.
When you talk about the safety precautions they're encouraging, how is all that working, and is there a way we could do it better?
So we have we have a faculty advisor. He's awesome. It's Dr. Kevin Shinpaw from the AOE department. We also have Bob Schoner, who works at the ADL, who's like a high power rocketry guru, basically. He's an awesome guy, helps us out a lot. We also have Dr. Pat Artis on as a assistant advisor, and we've had people from all over the school advise us, from like Ron Poff in the management department on our business end. And then also we have like Dr. Patterson, Dr. Young, Dr. Ball, like all sorts of people who have advised us and helped us out along the way on certain elements of the design. So that's been great. I don't want to speak like for the university because obviously it's kind of a touchy subject here, especially like the safety thing. Just given like things that have happened in the past with like the misfire and things like that. I'm not sure if you guys are familiar with that, but in my opinion, the moral of the story is failure is always an option as long as it's safe. Safe failure should always be an option, and it should always be a way to learn and rebound and come back stronger. Unsafe failure is just simply not an option with these rockets that are so big and so powerful. At that point, you're really just putting people's lives at risk, which is unacceptable. But I think what the university could really do is make a better distinction between safe failure and unsafe failure, and how those two types of failure differ, and how like learning from those two types of failure differ. Because you could do everything right with a rocket this complex, and the recovery system could still like not deploy because of a short circuit in the avionics, and the rocket will come down ballistic and land like on the farm or in the desert, wherever you are. You know, if you took the necessary safety precautions and followed like the IEEE Rocketry Association guidelines, you're going to be just fine. Your rocket's not going to be fine, but your team is going to be okay, and everyone's going to be safe. And you know, people might be sad for a little bit, but you're going to learn and grow from that experience, and your design is going to be a little bit better next time. Maybe you won't have a short circuit. You know, those kinds of failures allow growth to take place. And I think that viewing those failures that happen safely as more of a positive thing and less of a negative thing would maybe be a little bit of a smarter way to move forward in terms of like the university in general. Because we've had, you know, the incident with the misfire, which was an unsafe failure. And since then, we've felt in some cases, not all cases, that even safe failures have been punished in some by, you know, university faculty, basically, not any specific people, but yeah, like we used to be able to launch hot to 10,000 feet at Kentland Farms, and then it was 5,000 feet, and then someone's parachute didn't deploy, and then it was 3,000 feet, and then someone's rocket hit the power line, even though their parachute deployed perfectly at the power line, and now it's 2,000 feet. And at this point, we really can't do any of our like Skipper 1 launches at Kentland Farms anymore, even though we really wanted to do that. We're really limited to like small model rockets or level 1 certs. So and to be fair, there's a lot of politics going on with like farm managers and things like that over there that like I wouldn't even get into. But in terms of like the message we would want to send to the university, let people fail safely, and let people learn from that, because that's a really important aspect to doing anything in engineering in general, but specifically with these ambitious rocketry projects.
Yeah, I certainly agree with your ultimate statement there, right? If you're doing cutting edge, you're going to have a lot of failures, right? Because you don't go into it knowing everything. If you did, it wouldn't be cutting edge.
Exactly.
I agree with the need to fail sometimes, and boy, I've accomplished that in spectacular ways several times.
Yeah.
But I do advocate erring on the side of safety, so I don't want to sound like I'm disagreeing with any of those rule changes. I don't know enough about it to comment, but I would like us to be more of a help, if that's possible. We could talk about that offline somewhere.
Yeah.
I'm not the one to advocate backing off on safety rules, but
oh yeah, no, neither are we.
Yeah, neither are we.
But yeah, definitely. Let us make it clear that we are absolutely not advocating for backing off safety rules. We're just advocating for like when those safety rules are in place, trust the safety rules, and if people fail under those safety rules and it's safe, that's not a bad thing.
I certainly agree with the statement. Let's talk sometimes if you're up for it. And if there's a way
we'd love to.
can help, we would love to do it.
Absolutely.
So I maybe one question and maybe kind of a comment on the business side, and maybe you touched on it, you didn't mention it. But one thing I think that's, I just kind of wondering if you have in your team, you said, you know, don't overlook the business part of it, is one that's kind of in between of those. Do you have anybody who's done kind of like project management type thing of, you talked about like systems engineers, but there's sort of like project management, and it wouldn't be, you know, necessarily a huge thing, but I don't know if you've had anything like that.
Yeah, I can answer that. So we obviously that part of the team itself is completely necessary. We haven't found it yet necessary to allocate a specific team or a specific part of a sub-team to that. We've actually more looped the sort of project management role into the leadership role, which is the reason why we have multiple co-presidents. The way that our leadership system works is that we have 2 co-presidents and a vice president, as well as usually a trainee that's training up to either be vice president or co-president. And there's usually enough engineering expertise within the leadership and within the leaders of each sub-team to cover the necessity for a project management role. Recently, we've looked into sort of splitting the presidential roles into more of a chief engineer role and then a project management role. So we have that covered, and we haven't quite thought it necessary to allocate an entire sub-team to that.
Okay. Yeah, it's more a curiosity if you have had it or found it necessary. And then a slight comment, or probably, so we have it up here, the avionics. If you're ever looking to do testing, we're not certainly at the altitudes you're looking at, but I've been working on doing like high altitude ballooning, actually out of Kentland. So if there's any, it piqued my interest because you're talking about the long range comm systems, right? So we can get, the balloon up to 100,000 feet, kind of thing. It's a fairly, well, at least was a fairly cheap proposition to do, but these days we have to maybe relook at things because helium has been a little difficult to come by.
Right.
Yeah, if just a comment, if you're ever interested in saying, all right, well, what happens to this system when we go up? Yeah, you could talk it, flying a, little widget or something or whatever you've got on the string. So,
Yeah, that would be
That'd
awesome.
be awesome.
Yeah. Totally do that.
Any other questions online or here in the room or anything? Any other last words you want to?
Pretty much covered everything.
Yeah, I think that's about all we can say at this point.
All right. Well, thanks everybody for joining. We'll wrap up here, and thank you so much for presenting.
Thanks for having us.
Yeah, no problem. And we'll have another seminar here in 2 weeks, maybe at the 2 p.m. I have to work out with the presenter on what time's good with them, but we'll do this again in 2 weeks. So.
Great.
Awesome.
Thanks so much.